Hi, and thanks for coming to my talk. So the title of the talk is Comparing Computational Entropies Below Majority, or When is the Dense Model Theorem False? And this is based off of joint work with my advisor, Russell Impagliazzo. So the starting point for this work is something called the dense model theorem. And this is a result in pseudo-randomness with kind of a surprising number of applications to different areas. So the first context it appeared in was additive number theory. And here, and this was due to Green-Tao and Tao-Ziegler. And they used this to study kind of the presence of arithmetic or maybe generalized arithmetic progressions or some types of generalizations of arithmetic progressions in the prime numbers. Okay, and this was later imported kind of to the theoretical computer science community by Reingold, Trevisan, Tolsiani, and Vadan. And they observed kind of a consequence in sparse graph regularity. So there was also applications of this idea to computational notions of differential privacy. And this Reingold et al. Paper also observed a number of interesting connections between the dense model theorem and hardness amplification. And that will be discussed in a fair bit more detail. Okay. So now I'll describe what the dense model theorem actually says. Okay, so we start with a small set, and this is over a finite universe U. Okay, and here on the picture on the bottom, maybe S is sparse in some sense. And what the dense model theorem does is it gives us sufficient conditions for S to have a so-called dense model. And what I mean by that is there'll be some set M, which is large, or maybe we might say dense. And it's indistinguishable from S according to some tests F. Okay, and that's what I mean by modeling. So M kind of looks like S according to F. And these tests will just take points in the universe and produce some value between 0 and 1. Okay. So to formalize this, we'll just introduce a definition. So two random variables, x and y over u, are epsilon indistinguishable with respect to this test class F. Whenever this quantity here is bounded by epsilon. And so what's this quantity? So, well, on the inside, this is just saying what is the difference between kind of the average value of f over x and the average value of f over y, okay? And so for this entire quantity to be small would mean that kind of every f in big F kind of doesn't kind of assign significantly more weight or significantly more mass to x than y. Okay, so bringing this definition back to our informal description from earlier, so the dense model theorem gives basically sufficient conditions for S to have a delta dense epsilon model. Okay, and by delta dense, what I mean is just simply that kind of drawing a random point in the universe, you'll get something that lands in the set with probability at least delta. And by epsilon model, I mean kind of in terms of this indistinguishability that we just defined. So I want to say that S and M are epsilon indistinguishable by F, and we might shorthand that by saying M is kind of an epsilon model of S with respect to M. Okay, and I'll mention that this idea of having a delta dense model is equivalent to this to a notion called the Hill pseudo-entropy. Okay, and this was used at least implicitly in Hostad, Impagliazzo, Loop 11 to construct PRGs from one-way functions, and it was considered kind of more explicitly in a paper by Barak, Shaltil, and Winterson. Okay, so now so we've discussed kind of what the conclusion means to have a delta dense model. Now we need to kind of talk about what these actually sufficient conditions are. Okay, so kind of at a high level, the sufficient conditions for S are going to just be weaker pseudo-randomness conditions with respect to a new test class F prime, a parameter epsilon prime, a non-negative parameter, and as well as kind of our delta from before, okay? And so we'll define F prime in terms of a function G, which will take K points in 0, 1 and map to an output in 0, 1. And F prime will just simply be kind of the composition of G with elements in F. So what I mean is just you pick K elements in F, excuse me, and then you apply G to their evaluations, okay? And two examples that are worth keeping in mind are G being a product, okay? And this will, and this was used in maybe kind of the green tau setting. And majority, and this was used kind of in the RTTV or Reingold et al. Setting, okay? And in this latter case, we're thinking of maybe our Fs as being Boolean valued, so that way, G's domain is Boolean. Okay, so kind of continuing, what we want these sufficient conditions to capture is something that intuitively we'll say that S basically looks delta dense to F prime and with some error tolerance epsilon prime, okay? And of course, kind of looking delta dense, this can't just mean having a delta dense model, because then we wouldn't have anything to prove. Okay, and it turns out that there are two kind of different sufficient conditions which work. The first one, also kind of the what was used in green tau and tau Ziegler, has a shortcoming of requiring that epsilon prime is exponentially small of the parameters epsilon and delta. Okay, and so this is kind of a weak point of this particular formulation of the dense model theorem, or the particular formulation by green tau and Ziegler. And the second sufficient condition is able to get epsilon prime to not be so small, but in order to do so, it will actually need to use G, which is a majority. So recall kind of earlier G, or like in this case, G is actually going to just be a product. But now epsilon prime will kind of be epsilon delta, okay? And so what we'll, kind of skipping to the punchline, we'll actually show that this type of trade-off between epsilon prime and G is actually necessary. Okay, so now I'd like to try to motivate studying the trade-off between G and epsilon prime by looking at an application in de-randomization. So to begin, a major problem and a major kind of guiding question in complexity is basically to build pseudorandom generators for small circuits. Yeah, so this is not. Okay, so next I want to motivate the dense model theorem a little bit more from the point of view of building pseudorandom generators. So in this situation, we'll have, so our universe will just be the n-dimensional hypercube, and our tests will be small circuits. Okay, and so one of the kind of major problems in complexity is to build pseudorandom generators for small circuits. And by pseudorandom generator, I mean a function G, which will take a so-called like seed of length S, and it'll map it to some output of length N. And the hope will be that if I look at kind of the distribution that G induces on the n-dimensional cube, when we apply a uniformly random seed to G, we'd like this to actually be kind of epsilon indistinguishable from the uniform distribution over the cube, at least according to these tests F. Okay, and this has, the kind of most, famous application of this is de-randomization of BPP. Okay, and one of the primary approaches that's been studied is kind of this hardness versus pseudo-randomness idea. And here, what we would do is start with a hard function f, and by hard I mean that kind of no small circuit can compute f at more than, say, a gamma fraction of the inputs. And here this probability is just the counting measure. Okay. And so this, so kind of this is studied kind of in both cryptographic and in these de-randomization settings, is to build pseudo-random generators out of hard functions. Okay. So one of the kind of main successes of this line of inquiry is, well, I mean, it is de-randomizing BPP from a strong enough circular lower bound. And the kind of, a partial view of the framework is they basically start with a function, which we'll just think of as being delta hard. So they can really start with a worst case hard function, but we'll just think of delta. And so one step, and this was kind of accomplished, at least for the purposes of de-randomizing BPP in Impagliazzo-Wigderson, is this hardness amplification step. And hardness amplification will basically take a delta hard function and it will produce a function which is significantly harder, but oftentimes we'll think of maybe the hardness as being with respect to a slightly smaller test class. Okay, and then it's known, it's been known since the paper of Nissan and Wigderson how to actually produce a PRG from a sufficiently good average case hardness lower bound. Okay, so an interesting kind of property of this approach is that it kind of incurs this necessary computational overhead when we do this hardness amplification part. So specifically, or at least one way of understanding this computational overhead is that in order for this hardness amplification step to work, we need to basically start with a class F, which is closed undertaking majority. Okay, and this follows basically from, so this is true modulo some additional details, which I'm kind of just glossing over for now, but so this type of result is kind of due to Shaltil, Viola, and more recently a paper with Grinberg, Shaltil, and Viola. Okay. So a reasonable question is to say, like, can we avoid this overhead in case we want to de-randomize classes which aren't closed under majority? And one suggestion I'll make for now is an approach of Sudan, Trevisan, and Vidon. And what they do is they start with the same hypothesis of having a delta hard function, but now instead of doing hardness amplification, they'll actually produce a set which is indistinguishable from a delta dense set. So in particular, they'll produce a set with a dense model. Okay, and once they have a set with a dense model, they show that actually applying a randomness extractor will produce a pseudo-random generator. Maybe an additional suggestion, which is worth making, at least in this context, is we could also imagine maybe starting with some S which satisfies the dense model theorem hypothesis, use the dense model theorem to translate it into one of these delta dense sets, and then apply the extractor. And so I've kind of glossed over the extractor part, but the point is that we really can't, we don't, like, in order for the extractor part to work, it needs to be a delta dense epsilon model, okay? And this is kind of like, so we can't really have a weaker notion, or as far as we know, we can't really have a weaker notion of computational entropy that we can extract from to get pseudo-randomness. Okay, and the you know, connecting this picture back to our work, we're able to show that kind of similar to the overhead that's necessary for hardness amplification, there's also going to be some barriers to implementing these other strategies below majority as well. Okay, and this is relevant if we're, say, trying to construct pseudo-random generators for AC0 mod 2. Okay, so now having given some background and motivation, I'll describe the dense model theorem in some more detail. So kind of starting with the conclusion, we're looking for a delta dense epsilon model. And we have three sets of parameters. And the kind of green parameters are the inputs. So so this is kind of what we start with, and so S is kind of the set we want to model. This output, if there is one, is just going to be the dense model. And then these preconditions are kind of the important part as far as the sufficient conditions are concerned. So the preconditions will say, kind of given SF, epsilon, and delta, how and kind of what types of pseudorandomness conditions does S need to satisfy in order for the dense model theorem to be true? Okay, so the first condition of this type, and this was the assumption that was used in Green Tau and the related work with Ziegler. So their assumption was that S is basically delta dense inside of a pseudo-random set, okay? And by pseudo-random set, I mean, so there's going to be some set T, and it'll have the property that it's epsilon prime indistinguishable from the uniform distribution with respect to these tests F prime. And additionally, S will be delta dense in this set. So if I draw a random element from T, I'll get an element from S with probability of least delta. Okay, so this is the first sufficient condition. The second sufficient condition is known, so I'll refer to it as epsilon delta pseudo density. And this condition can be phrased in a number of equivalent ways, but so I'll define it in the following way. So a set S will have epsilon prime delta pseudo density with respect to this test class F prime. If basically I can build a delta dense set which fools any particular F prime or F and F prime into thinking that it's S. And so specifically, so you, so basically I'll give you an F prime, an F and F prime, and using knowledge of F prime, you can, all you need to do is construct a delta dense set so that F can't tell the difference between S and M. So basically, you know, their expectations are close. Okay. So this seems like a, you know, kind of perhaps a pretty weak condition, given that the dense set gets to depend on F. But it turns out to work to apply the dense model theorem kind of with the right restrictions on F prime and F. Okay. So, okay, so using this picture, I'll kind of maybe try and summarize the different dense model theorems now using this table. Okay, so once again, there are kind of these two different types of dense model theorems generally. And the first one basically makes this dense inside of a pseudo-random set assumption. It produces, it uses G, which is a product, and it uses epsilon prime, which is exponentially small, and the other parameters. The second type of dense model theorem will now use this weaker assumption of pseudo-density, but what it needs to pay, so it'll use this weaker assumption of pseudo-density, and it'll obtain an epsilon prime, which is actually going to be like epsilon times delta. Okay, but it needs to pay in kind of how complicated G is. So now it needs to be a majority. Okay, so before so to remind you of our results, we're basically going to be able to show that, if we want epsilon prime to be some polynomial in epsilon and delta, then G will have to be relatively complicated. So it might not have to compute majority, but at least you wouldn't be able to do it if, say, G was a constant depth circuit. Okay. But before discussing our results in more detail, I want to kind of explain why you might expect majority to pop up when you try to prove the dense model theorem. Okay. So I'm going to kind of like completely hand wave the proof idea, and I mean, this isn't really the complete idea, but I just want to give you just some exposure to why you might expect majority. Okay, so here we're going to be trying to prove that kind of the second sufficient condition implies a dense model. And we'll actually do it by the contrapositive. So we'll assume that there aren't any dense models, and then we want to show that the second condition is violated. Okay. So when you write down the definition, or what it means to not have a dense model, this is what you get. So every delta dense set has some distinguisher between S and M. Okay. And the kind of crucial observation is that we can apply LP duality to this statement. So we can basically think about this as a game, and the game is between the measure player, or kind of the model player, and the function player. Okay. So by applying LP duality, min-max, or however you'd like to describe it, we can kind of switch the order of play if we allow randomization. Okay. So what that means for us is that kind of under the circumstance that we don't have a dense model, it's actually the case that there's going to be some distribution over our test class, which distinguishes between S and every delta dense M on average. Okay. So we can kind of switch the order of the quantifiers in some sense by using randomness. And then to get from here to majority, the idea would be, well, we'll sample a bunch of independent copies of F tilde. So this is a small typo, so it should be F tilde. And then we basically like to argue that if we take the majority of those independent copies, then it will be able to distinguish S from any delta dense set. Okay, and the idea there would be using some type of Chernoff bound, to say that, if I take a bunch of independent samples, then kind of the value should still be, should still be very close to this with high probability. But so hopefully that explains why the majority can come up, and maybe, so somehow the majority helps us kind of aggregate, maybe these observations, which are individually a little bit noisy or not so useful. And so what we actually can do is say that the usage of majority is, so we're not going to be able to say that it's necessary, but we're going to be able to say that there are kind of classes which don't compute majority for which this actually fails. Okay. So the first example will be kind of using the first assumption of being delta dense and epsilon pseudorandom set, and it will kind of compare that to having a dense model. And we'll show that there are distributions which satisfy this hypothesis, but fail to satisfy the conclusion. So in particular, we'll build this distribution D1, and it will be delta dense in an epsilon prime pseudorandom set. And in this case, we're thinking of our tests as being depth D circuits with size basically kind of sub-exponential in 1 and 2D. But we'll also be able to show that this doesn't have a delta dense epsilon model. And actually, it'll just be with respect to bit tests. So bit test will just kind of take the input and just output the ith bit. Our second result kind of extends, so our second result concerns kind of the comparison between the two types, or between the two sufficient conditions. So in fact, you can show using kind of one of the equivalent definitions of pseudodensity that this kind of first condition pretty readily implies the second condition of pseudodensity, okay? And what we show is that this kind of and so you would also see kind of by the dense model theorem, the converse is true, at least when you're closed under majority. But what we show is that it can also fail when you're not. So we show in AC0, this can fail. So AC0 being constant depth circuits polynomial size. So specifically, we'll construct a pseudodense set, and it'll be pseudodense against depth D circuits of a size, kind of exponential and maybe 1 and 2D. And it will also be able to maintain that it doesn't have a delta dense set. It's not delta dense in any epsilon pseudorandom set where now the tests can compute kind of the parity of any two bits. So our next result, it kind of can extend or concerns a different model of computation. And so here we'll also be able to separate the sufficient condition, these two sufficient conditions, but now it will be with respect to low degree polynomials. So what we can show is that we can find sets which are pseudodense for low degree polynomials. And here the field really doesn't matter, just that it's finite and its characteristic is constant. And but we'll simultaneously get the property that it's not delta dense in any epsilon pseudorandom set, again with respect to these kind of parity of two bits tests. Finally, we can prove a slightly more general result, which says that if we have a test class F, so that we couldn't use kind of F oracle gates in a constant depth circuit which solve majority, then it actually will have pseudodensity of this type. Okay, and then we can use, and then once again we can finally extend that to say that it's not delta dense in epsilon pseudorandom set. And this, this is going to draw heavily from the work of Chaltiel and Viola, who show something quite similar for hardness amplification. Okay, so I also want to mention the relationship between the dense model theorem and the hardcore lemma. And part of that is because it'll explain some of the motivation in terms of de-randomization from earlier. Okay, so the hardcore lemma is kind of a classical result in circuit complexity, and it says that if we have a n-bit Boolean function, which is delta hard for f prime, then there's actually a delta dense set, and actually, well, so it's 2 delta dense, thanks to Hohenstein. On which f is extremely hard for big F, which is we think of as slightly smaller than f prime, and actually we'll think of f prime as just being the majority of f's. Okay, so what does that mean? It says that there's going to be this dense set on which kind of this big F can't really do better at computing f than just guessing a random bit. Okay, and so this can be used, say, kind of to prove the Yau's XOR lemma. And another thing worth noting is that the known proofs actually do take kind of this f prime to be majority of f's. Okay, and in fact, this is kind of necessary in some for some kind of formulations if necessary. And this is due to Lu Tsai Wu and Chaltion Viola. So the other relevance of the hardcore lemma is that it's used in the Soudan, Trevis, and Vaudin construction of the pseudo-entropy generator from a delta hard function, okay? And the idea is to kind of use the hardcore, like to use this 2 delta dense set M as kind of, as the starting point for our pseudo-entropy generator. Okay, so this is the hardcore lemma. The thing that kind of ties it directly to our work is a claim by Impagliazzo. His claim says that if the dense model theorem is true for F, then so is the hardcore lemma. Okay, and I'm being vague, but there is a very strong connection, and the parameters are preserved. And in particular, this implication means that by disproving the dense model theorem in the context we disproved it, we also show that the hardcore lemma is false in these contexts. And as far as I know, these are kind of the first explicit counterexamples to the hardcore lemma below majority that have appeared in the literature. Okay, so as kind of a last part before concluding, I just wanted to mention just some simple technical ideas that get a lot of mileage in this paper. So the first one is relevant to showing that kind of a particular, or like a given set X doesn't have a dense model, okay? And the way that we do that is we'll use kind of a necessary condition of density. So this necessary condition says, if we have a delta dense X, so this is over kind of the n-dimensional hypercube, then the kind of average bit of a random string from the set is going to be close to a half, and kind of its closeness will be kind of determined by delta n in this way. Okay, so maybe it's easier to see what this means by a picture. So the idea is like, so say we're kind of building a delta dense set X, and we want to do it in a way that maintains that the bits are as biased as possible. Okay, so what we would probably start doing is, start at kind of one of the ends of the cube and start packing it and packing it and packing it until basically we got to like delta. Okay. And the question is, like how far do we get? And in fact, we get this far. Okay. And not only that, this is actually, kind of the best thing we can do. Like, so like, if we wanted to kind of maximize the average bias, the best thing we could do is basically pick this kind of Hammond ball. But in general, the idea is that since so much of the mass of the cube is very close to its center, in the sense very close to kind of weight n over 2 strings, the only way we can pick a lot of strings is by picking a lot of ones which are basically balanced. Okay, and this is basically a quantification of that, and it's also kind of like the same thing as like Cheng's lemma from analysis Boolean functions, and it's been used, like, and so this observation has been used in a number of places. Like Raz's paper on parallel repetition uses this idea, and then another good reference is kind of Mayer and Wigderson, who wrote a whole paper basically about this lemma. Okay, so it's a really nice reference. So the usefulness for us is that if we can design a set basically where every single bit, so say we have the set like S here, where every single bit has kind of is like is it greater, has has epsilon more bias than this kind of order square root log 1 and delta over n, then it would mean that S would actually be indistinguishable, or epsilon distinguishable rather, by any delta dense set X. Okay. So the hope would be, we want to say there are kind of sets S where every bit is very biased, or kind of extremely biased, but it still is actually pseudo-dense, so it still satisfies this like weaker pseudo-randomness condition. Okay, so this would kind of be the basic idea is to use this idea of constructing biased sets. So in order to extend this to saying that X isn't dense in a pseudo-random set, what we'll basically do is extend the previous observation to use kind of concentration. And now instead of looking for biased sets, what we'll look for is kind of sets which put a large mass on their tails. And by that I mean kind of like the tails of the random variable, kind of sum of the xi's is heavy. Okay. So we also need to kind of prove these unconditional pseudo-density results. And the way that we do that is by, so one way of framing that is we kind of solve this relative error version of the so-called coin problem. And the coin problem is something that's received a lot of attention recently in the pseudo-randomness literature. And this part will we end up using, drawing a lot from the work of Shaltil-Viola, Srinivasan, and Tal. Okay. So now, concluding, I guess I'll just ask maybe 3 questions, which I'd like to know some more about. So the first is, can we extract basically pseudo-randomness from pseudo-density? Okay. So recall that like STV showed that we can extract from dense models. But we showed here that, in order to go from pseudo-density to dense models, you need to pay a majority. Okay, so can we just avoid that and just extract directly from pseudo-density? So this has been studied recently. 2 very nice papers, so Duran, Moshkovitz, Zuckerman, and Chen and Tell. So they study this question when they're trying to get kind of super efficient hardness to randomness trade-offs. Okay, so the second question is just whether hardness amplification is actually just false under majority. So we know from this work that the hardcore lemma is false in some cases. And we also know, a lot of limitations of hardness amplification related to majority from the work of Shaltil and Viola and Grinberg, Shaltil, Viola. But we'd like to know, could you just prove unconditionally that this type of amplification couldn't work? Okay. And finally, are the hardcore lemma and the dense model theorem equivalent? So recall kind of Impagliazzo shows that the hardcore lemma implies the dense model theorem, but the other direction is still not known. Okay, so that concludes the talk, and thanks for listening.